Object. I mean, as distinct from created First of all,
God morgon och varmt välkomna här till dagens disputation. Både ni som är här i salen och ni som deltar via Zoom. Det är en hybridmöte som vi har här idag. Campillo har författat sin vetenskapliga avhandling med titeln Deviations from the London Model in Superconductors som hon kommer att presentera idag och försvara. Jag har äran att presentera dagens huvudpersoner. Det är och vi börjar med själva respondenten, Campillo, som sitter här. Sen har vi fakultetens opponent som är Dr. Sebastian Mühlbauer, som är med oss via Zoom här idag. Välkommen Sebastian. Han är från Technisches Universität München och från forskningsneutronskällan Heinz Meyer-Leibniz, också i München. Välkommen. Vi har 3 ledamöter i betygsnämnden. Vi börjar också med Jasmin Sassa, en ledamot som också deltar via Zoom här. Kommer från Jasmin. Jasmin är från Chalmers tekniska högskola i Göteborg. Sen har vi 2 ledamöter som deltar här i salen. Se om vi kan se dem. Nästan. Det är här har vi dem. Det är Diego Alba-Venero från the ISIS Neutron and Muon Source Rutherford Appleton Laboratory i Storbritannien. Välkommen. Och sen är det professor Martin Leinze här från Lunds universitet, fakultet ämnesfysik. Vi har också en suppleant i betygsnämnden i fallet att någon av andra ledamöter inte kan vara med. Det är Rasmus Petersen från DTU, Danmarks tekniska universitet, Köpenhamn och också från ESS. Vi också är med oss. Dessutom så har vi se om vi hittar er. Har vi Emmas handledare. Nu ses ni här. Det är huvudhandledaren professor Elizabeth Blackburn från Lunds universitetsavdelningen för supertronusfysik. Biträdande handledare Dr. Rasmus Westerström, också här samma avdelning. Och jag hoppas att vi också har med oss Emmas tidigare handledare, biträdande handledare professor Ted Foden, University of Birmingham. Välkommen. Tack att du kan vara här. Själv heter jag Rainer Tim. Jag är universitetslektor här på fysik vid Lunds universitet, föreståndare för avdelningen för supertronusfysik, jag är ordförande för denna disputation. Själva disputationen hålls på engelska. Therefore, it's time now for me finally to switch to English, making it easier for both you and me, I guess. So what will happen here today? What will be the course of this day? I think you all got a copy of the thesis. Otherwise, there are still a few copies available here. So the first thing is that Emma will be given the chance to announce any corrections errata to the thesis. Then we will hear the opponent, Sebastian Mühlbauer, with an introduction to the field. which might take about 10 to 20 minutes. Then Emma will present the summary, the highlights of her work, which might take 20 to 30 minutes, something like that. After that, we will have a short break, allowing everyone who needs to leave at that point to do that before we start the actual defense act, which will then start with the opponent and the PhD candidate discussing the work in detail. After that, all members of the examination committee will ask questions. And then finally, also everyone else in the audience, both here in the room and also via Zoom, will have the opportunity to ask questions. Then, after that, the defense will close. The examination committee will gather in a separate room here and discuss the outcome of the examination. And then we will directly announce the decision in the group room of our division, where I think that Emma has also prepared something for all to gather there, but that will come later. So now, last thing for me to say is it's time for you to switch off your mobile phones or turn them to silent mode at least. And then it's up to Emma so that you can start with mentioning any errata, any corrections to your thesis.
So I would like to present the errata given here. First of all, I would like to announce that 2 days ago, our paper 5 was finally published on Physical Review B. And also, I would like to mention some mistypos regarding to the units or regarding to figures. Also, it's important to remark in page 12, that is the modulus of the incident vector is conserved with the modulus of the scatter vector. And also it's important to remark in page 35 that the gap to is 0.7. And another important remark, it's like in the conclusions of the chapter 4 in page 76, I mentioned a 5% dope calcium dope eco, but indeed it's a 4% calcium dope. Apart from that, there's typos regarding to figures labeling and some words that has been misspelled.
Thank you, Emma. With this, now it is time, and let me change here. Stop sharing at this point. And it's time for our opponent. Yes, here we have you, Lars. Thank you for serving us here today. So please give us an introduction to the field of the work.
Great, thank you so much. So I will start sharing my slides. Let's see if that works. Give me a second. You have to allow me sharing my screen first. Now it works perfect. Great. So then. Great. You do see my slides?
Yeah.
Perfect. Great. Thank you so much. So first of all, thank you all for inviting me, and this is a really great honor for me to do that. That's the first time I do this in Sweden, so I guess I'm similarly nervous to you, Emma. But I'm really looking forward to do that, and it's a great thesis, and it was a pleasure reading it. And it's also nice to see and hear so many familiar voices and faces. And it's just a pity that I'm not in Lund at the moment, which is mainly due to an experiment at PSI, which was unfortunately cancelled in the last minute. And I've seen a red shirt, so Ted, hello.
Hello.
Okay, great. So let's start. So I'll give you a brief introduction into superconducting vortex matter as seen by Sands for Emma's PhD defense. And so I'll give you a brief introduction to the following points. So I will briefly touch the basic concept of small angle scattering. So that's a technique Emma has used quite extensively in her thesis. Then I'll give you a brief primer into magnetism on the nanoscale. So why magnetism is interesting on the nanoscale. And then I'll give you an introduction into superconducting vortex matter and what can be done in general using small angle scattering to look at superconducting vortex matter. So we'll briefly start with the basic concept of small angle scattering. So as you all know, if you want to look at large correlations in real space, so the nanoscale regime, let's say 20 angstroms to around 40,000 angstroms, that goes along with very, very small scattering angles if you just look at Bragg's law, and therefore goes along with small momentum transfers, Q, so in the range of 1 reciprocal angstroms to 10 to the minus 4 reciprocal angstroms. And so small angle neutron scattering, that's nothing else than a very special diffractometer that is specialized to resolve these very small scattering angles. So the scattering angles then range typically from 20 degrees or 30 degrees down to 0.01 degree. If you take typically cold neutron wavelengths of 3 to 12 angstroms. So small angle scattering is looking at very large structures in real space, and a typical instrument schematics is shown here in the lower view of the slide. I just switched to the laser pointer. So what we typically we have a neutron source somewhere here. We have a white neutron beam. And then the wavelengths or the speed of the neutrons is selected by a velocity selector. And then the instrument is essentially divided into two sections. So we have a collimation section, which is just a set of neutron guides and collimators to prepare a parallel neutron beam. So you need a very special parallel beam to resolve these tiny scattering angles. And then the second half of the instrument is essentially an evacuated scattering tube with a two-dimensional position-sensitive detector, which is there to record the scattering pattern. So essentially, small angle neutron scattering, that's very simple instruments. They're very large and kind of expensive, but the principle is very simple. So why to look at magnetism on the nanoscale? And this is just shall give you a very brief overview on why magnetism is interesting on the nanoscale. And this essentially splits up into two parts. And one part on the left-hand side, I call this magnetism of material that are inhomogeneous on the nanoscale. So that's typically you have a material that is inhomogeneous on the nanometer range, and the magnetism of that material is imprinted by the inhomogeneous material parameters. Typical examples like nanoparticles, ferrofluids, all the commercial magnets, so neodymium iron boron magnets, which are around. Also recording media, nanodots, and magnetic steels. But that's not of interest for today. So today we'll focus more on the materials that are on the right-hand side, where we have homogeneous materials. So the material itself is homogeneous, but there's an emergent nanoscale magnetism that emerges due to the electronic correlations of that materials. So typically, examples are skyrmions, complex charge and stripe order due to ferromagnetic or antiferromagnetic interactions or competing interaction. And this is the topic Emma is going to talk today, and I will give you a brief insight in the next slides. This is superconducting vortex lattices. So typically these are structures that are inhomogeneous magnetically on the nanoscale, but arise due to the electronic correlations of a material. And superconductivity is the prime example. So we see that here on the bottom right, we have this very, very nice and very old decoration images of the superconducting vortex lattice seen here on the surface of an niobium sample, where you see the hexagonal pattern of the vortex lattice. And this is what I'm going to briefly introduce you in the next slides. So superconductivity. Superconductivity, that's a phenomenon which is actually quite old, so about 110 years old, was discovered by Campillo in 1911, and is characterized by two effects. So first, you have the total loss of resistivity, what we see here when the resistivity of mercury is plotted, and you have the critical temperature here of 4.2 Kelvin, where the resistivity drops down to 0. And the second effect is the so-called Meissner-Ochsner effect. So superconductors are ideal diamagnets, so they expel the magnetic field independently how you enter the superconducting phase. And therefore, this is really your own thermodynamic phase superconductivity. If you put a superconductor into a magnetic field, the superconductivity is characterized by 2 length scales. One is the London penetration depth, which characterizes the scale on which a superconductor expels the magnetic field. And the second one is the coherence length, which is the sort of the rigidity of the superconducting phase. And both of these length scales can be assigned to an energy or to a surface energy of a normal to superconducting interface. So if you have an interface from normal conductivity to superconductivity, of course, it costs the superconductor energy to expel the magnetic field. On the other hand, the superconductor gains energy if he can condense electrons to Cooper pairs. And by looking at this interface energy, which is assigned to that interface, we can split the superconductors into two parts. So one is called type 1 superconductivity, where the magnetic field is expelled until we have critical field. And the second, the larger family of superconductors, and this is the more interesting family, that's the type 2 superconductors. And these type 2 superconductors, the phase diagram is shown here on the right-hand side. They split up into 2 phases. So we have the temperature and the field axis here, and we have the Meissner phase where the superconductor expels the magnetic field, and we have the so-called Shubnikov phase where the magnetic field enters the superconductor in form of superconducting vortices. So the superconductor wants to maximize the interfaces between normal conducting regions and superconducting regions, and therefore the solution was found by Abrikosov. What happens is you have a small normal conducting area which carries the magnetic field, shielded by a supercurrent, and this normal conducting area is called a superconducting vortex. And this, due to the quantization of the magnetic flux, each vortex carries exactly 1 flux quantum. So this is the vortex flux quantum h/2e, and this is the flux of a superconducting vortex. And it's geometrically shown here. So we have the core of the vortex, which is normal conducting, and then we have the superconducting circular current, which shields the vortex. And so the fun thing with these vortices is that these vortices are magnetic objects that arise on a completely homogeneous sample. But these magnetic vortices, due to the quantization of the magnetic flux, get particle-like properties. And of course, as particles arrange in a regular lattice, these vortices arrange in a so-called vortex lattice. And this was found actually by Abrikosov, that these vortices arrange in a regular 6-fold lattice. And we see that here in the decoration images, where ferromagnetic powder is evaporated in vacuum, and the ferromagnetic powder then sits on top of each vortex. So these vortices behave like particles, they interact. And what is found is that these vortices behave like particles, and we can do superconducting vortex crystallography. As we do crystallography on condensed matter, we also can do crystallography on superconducting vortex matter. And this is essentially what Emma has been doing in her thesis. And so with this slide, I want to give you a brief overview on how to detect and how to look at vortex matter. So this is a slide I stole from a PhD student of mine, and this summarizes several techniques on how to look at a vortex matter. So we can have here, we have the decoration images, where you evaporate the magnetic powder. We can do Lorentz microscopy to image the vortices, scanning tunneling microscopy, holography, squid, MFM, and magneto-optical imaging. And the color code behind these images sort of represents to what the measurement technique is sensitive. And what we see here is we have small angle neutron scattering, and small angle scattering in a way sticks out that we are sensitive to the bulk of the superconducting vortex lattice. So we're not only looking at the surface. Most of these techniques only look at the surface of the samples, but with small angle neutron scattering, we are really able to look at the bulk of such a superconducting vortex lattice. And that's why SANS is very useful to do vortex lattice crystallography. And this is exactly what Emma has been doing. And so how does it work? Well, a vortex lattice for a neutron is just a large-scale magnetic Bravais lattice. So these vortex lattices have Bravais properties, and therefore a vortex lattice can be seen as a diffraction grating for neutrons, very large scale, but it's essentially very simple. So the setup is typically shown here. So we have an incoming neutron beam, and the incoming neutron beam is diffracted at the vortex lattice, and then on the detector we see a diffraction pattern of our vortex lattice. So we see the picture of the vortex lattice not in real space, but in reciprocal space. And as the lattice spacing of the vortex lattice just given by the magnetic field, we get a very simple relation of field and scattering angle and the reciprocal lattice vector. And I've gave you here some typical values. So for a pretty low field of 150 millitesla, we get a lattice spacing of roughly 1200 angstroms, which leads to a very small Bragg angle of roughly 2/10 of a degree, I think. The intensity of such a Bragg peak, and this is really a Bragg peak, so that's not a diffuse small angle sketching, but a Bragg peak, is mostly given by the form factor, and this is in turn given by the shape of a vortex. So what we see here on the detector, if we do a rocking scan, so we rotate the sample, therefore we rotate the reciprocal lattice through the Ewald sphere, and then we sum up, and then we get a very nice picture in reciprocal space of our vortex lattice, which directly gives you the symmetry of your vortex lattice in your bulk crystal. And as the vortex lattice is a 2D lattice, this is just a rotation of 90 degrees around the beam axis to go to the real space lattice, to get the symmetry of your real space lattice. So why is this useful? And this is one of my very last slides. So why is it useful to do vortex lattice crystallography, to look at vortex lattices by means of small angle neutron scattering? Well, there are multiple influences on the vortex lattice symmetry, and this is of course influenced by the vortex-vortex interaction. And these influences can be like crystal or the Fermi surface anisotropy. It can be the gap symmetry, so looking into conventional or unconventional superconductivity, and it can be non-local corrections, for example, that are temperature and field dependent. And a very simple example I chose here, and I guess everybody knows that, and also Ted, you know that. This is niobium, which is a very simple S-wave superconductor. And in niobium, you get very nice frustration effects where you when you apply the magnetic field along a 4-fold crystal direction. And then there are several ways of putting a 6-fold vortex lattice on your 4-fold crystal axis. And you get really very nice different vortex lattice symmetries. So this is really doing a diffraction experiment, a crystallography experiment on this superconducting vortex matter. There are, of course, more examples where this has been done. One example is also very nice, is that looking at YBCO, where also a deviation of the ideal 6-fold vortex lattice symmetry has been found. And YBCO, that's one material where Emma has been working on. Then, of course, looking at the gap symmetry, looking into unconventional superconductivity, very nice example is the work that has been done on the uranium platinum 3 compound, where depending on where you are in the superconducting phase, different symmetry of the vortex lattice has been found that, of course, reflects the symmetry of the superconducting gap. So by looking at the symmetry of a vortex lattice, we can distinguish like gap symmetry, Fermi surface effects, but we can also look at the temperature and the field dependence of the structure factor and the form factor, which is the temperature and field dependence of the penetration depth and the coherence length. We can look at the crystalline quality of a vortex lattice, as we do when we do a regular diffraction experiment or a crystallography on real single crystals. So this is an example where this is potassium iron arsenide superconductor, where we did the crystallography on the vortex lattice to extract the correlation lengths of the vortex lattice. And I guess by this, the time is almost over. So I hope I could somewhat set the stage for your talk, Emma. I'm absolutely looking forward to hear your talk. And I guess you will tell us more about how to use small angle sketching for much more vortex lattice crystallography. So with that, I thank you all for your attention, and I'm really looking forward to your talk, Emma.
Thank you very much.
And I guess I have to stop sharing this.
Okay, then the next step is that Emma will present the highlights of her thesis. Sure that I don't see you.
Well,
Sorry.
thank you. Well, good morning, everyone. My name is Emma Campillo. Thank you all for coming and attending to my talk. So during this presentation, I will present the work that we have been working during the last 4.5 years that I included in my thesis, deviations from the London model in superconductors. Before starting, I would like to thank all the help provided by supervisors, Elizabeth Blackburn and Ted Folgan. And also I would like to thank all the help provided by students, postdocs, and also our collaborators in the different research facilities that we perform our experiments at ILL, PSI, and HZB, which are going to be experiments that I'm going to explain right now. So I will try to be a little bit quick, since Sebastian already gave an excellent introduction of what superconductivity is about, and also what neutron scattering can help us to observe this kind of materials. But apart from giving this brief introduction about superconductivity and small angle neutron scattering, I will also explain why are we interested, or why we look at polypermagnetic effects in superconductors, and also our studies on the high temperature superconductor yttrium baryon 2 copper 3 oxygen 7, that from now I will simply call it ITCO. So many of you will be asking yourself, what is superconductivity about? So if we look to the Oxford Dictionary definition, it's the property of zero electrical resistance in some substances at very low absolute temperatures. which means that in our everyday life, we usually use copper wires, and these materials, they usually show some resistance to the electrical current. However, we have certain materials where when we lower down the temperature down to a specific temperature, where we call it critical temperature, we found out that these materials have absolute zero resistance against the electrical current, such as it was the case that it was first discovered in 1911 in mercury, and these materials are commonly known as superconductors. Usually, apart from zero resistance, they show a perfect diamagnetism, which allows us to create big magnetic fields that can be used in several things that helped us in our everyday life. For example, in magnetic resonance imaging. Also, it is used for guiding the trajectory of particles in particles accelerators as the CERN. They are a key part on developing new technologies to contain the energy that will be created in future nuclear fusion reactors. They also use in squids, and also they are used in superconducting magnets that we use for our own experiments, as our 17 Tesla magnet that we have been using in some experiments that I'm going to present now. So, as Sebastian explained before, essentially we have two types of superconductors. On the left-hand side, we have what we call the type 1 superconductors. So the particularity about these superconductors is when we apply a magnetic field between 0 and an upper critical field, they are able to expel the magnetic field completely from them, which means that the material is able to create a magnetization which is equal and opposite to the magnetic field that we are applying to it. And then the magnetic field inside this material is 0. So that's why it's able to completely expel the magnetic field that we apply. And this effect is usually known as the Meissner state. However, when we move on to type 2 superconductors, these superconductors, they are also able to expel the magnetic field between 0 and a lower upper critical field. And they also show this Meissner effect. However, when we apply a magnetic field between the lower and an upper critical field, the magnetic field is able to cross or pass through the sample in form of a vortex line lattice, as we can see in the little picture that we have here. When we increase the magnetic field that we apply to this material, the density of flux lines will increase as well, up to an upper critical field where the material will come back to its normal state. Right, so we are going to focus our attention on these type 2 superconductors and on the arrangement of these vortex lines when we apply a certain magnetic field. The particularity about them is that the magnetic field inside these flux lines, the magnetic field is completely quantized in magnetic flux quantums. There are only two characteristics lengths on these superconductors that are really important to characterize the superconductors, which is the coherence length that we will commonly know as psi, and can be understood as the vortex radius. And also we have the London penetration depth, which is the distance in which the magnetic field decreases exponentially. Then we can characterize this type 1 or this type 2 superconductors depending on the ratio between these two characteristics lengths that we have for the superconductors. So as I mentioned before, we will just focus our attention on type 2 superconductors. So an important feature that happens when we have superconductivity is that when we are in the superconducting state, the material develops a gap around its Fermi surface. This is well explained by the BCS theory. Following this BCS theory, our order parameter will be given by this superconducting gap. When the material is on its superconducting state, we will have this gap around the Fermi surface. However, when the material comes back to the normal state, it will be zero, and then it will behave as a normal metal. So, and the particularity about BCS theory, it only explains that this kind of behavior can be explained with the S-wave superconducting gap, which means that it's isotropic around the Fermi surface. So the materials or the superconductors that are able to follow the BCS theory and have an isotropic S-wave around the isotropic S-wave gap around its Fermi surface are commonly known as conventional superconductors. However, we will have some other materials that they do not show this isotropic superconducting gap around the Fermi surface. And they are going to be known as the unconventional superconductors, and we will focus our attention on these kind of materials. So unconventional superconductivity or superconductors can show other pairing symmetries for this developing superconducting gap, and they can show nodes, which means that the superconducting gap goes to zero in certain parts of the Fermi surface. So here we have a couple of examples of an S-nodal S-wave pairing or a D-wave pairing. Right, so now the question that comes up is, how do we study these materials? So as Sebastian explained before, when we are working on monochromatic neutron experiments, or in our case, in monochromatic small angle neutron scattering instruments, we usually have a neutron beam with several energies or wavelengths. Then we have a certain velocity selector. We will choose a particular wavelength that we are interested in. And after passing through collimators, it will interact with the vortex line lattice of our sample. I will remind you that the sample has been already cooled down below the critical temperature, and also we apply a certain magnetic field to have the superconducting phase on the material. So, since the neutrons carries a magnetic moment, they are able to interact with magnetic structures, and they will be able to interact with our vortex line lattice as well. So the diffracted neutrons will be detected by a two-dimensional detector, and the unscattered neutrons will be collected by a beam stop at the center of this detector. So as I mentioned before, we use neutrons because they have this magnetic moment, but also we use small angle neutron scattering because we can resolve structures with a big d spacing. So from vortex structures that looks like this on real space, we will expect a reciprocal space picture as the one that I show on the right-hand side. Okay, so once we have our experiment, we want to observe or obtain physical quantities that are going to help us to provide information or characterize these superconductors. Usually, we rock our sample around the neutron beam, and to fulfill the Bragg condition, I have a Bragg reflection on one particular point of the reciprocal space. So the information that this Bragg reflection can provide us is given by the integrated intensity that we can measure from this rocking curve. So if we express the magnetic field that it's passing through our sample, the Fourier components of this Fourier series is known as the form factor. And the integrated intensity that we measure in our experiments and the form factor are proportional to each other. So then we will be able to characterize this superconductor by the dependence of this form factor when we apply certain temperatures or when we apply different fields. So the usual expression that it's used to explain or to reflect the dependence of the form factor when we apply different magnetic fields to our material is the London model expression. The London model expression will be just this first term on the equation, but since we have the superconductors have a finite size of the course of the flux lines that are passing through the material, we will have to include a Gaussian cutoff to have this finite size of the course. So as we can see, this London behavior, or this decrease in behavior of the form factor with increasing field, can also be found in unconventional superconductors as the barium-based superconductor we are showing on the slide. And the other important feature is that using this London expression, we can manage to calculate the London penetration depth and the coherence length for a specific superconductor. This is the ideal case. But then what happens if we find out that the form factor is not behaving as we expect? So from our we measured the form factor of cerium coupled to silicon 2 at several temperatures and applying different magnetic fields. And surprisingly, we found that the form factor is actually increasing instead of being decreasing when one's approaching to the upper critical field. This is rather shocking, but we already found out this kind of behavior in other well-known cerium-based superconductor, which is the cerium cobalt indium 5. And this kind of behavior has been addressed to polyparamagnetic effects. So we have some data that can be proved that we have direct evidence of polyparamagnetic effects in the cerium coupled silicon 2. But we want a model that can describe this kind of behavior rather in temperature or rather in field. So following some numerical work that has been previously developed by Ichioka, this has been numerical calculations that were performed to simulate the form factor of cerium cobalt indium 5 and using different strengths of the polyparamagnetic effects. And we found out that the stronger the paramagnetic effects are, then we have a big peak that is showing up close to the BC2. However, when we do not have, or the polyparamagnetic effects present on the sample are negligible, the form factor comes back and behaves as the London model expression. So then we will arrive to several conclusions following these numerical calculations. One is that we have to base our model on the London model itself, and also including this Gaussian cutoff. And then when we have these unpaired electrons on the course, the magnetization is increased, and also it ends up breaking the superconductivity. And as a consequence of this increased magnetization, we also have an expansion of the core size with increasing field. So following these requirements to develop our model, we have that we can start from the London model expression that we found before. We still have our Gaussian cutoff to have this decay along field, but we included a paramagnetic term on this expression. On this paramagnetic term, we have to include the density of the flux lines that are present on the material depending on the magnetic field, the extra magnetization that is created, and also the expansion of the course that also depends on the temperature and the field that we are applying. So the remarkable thing about this model is that only 2 fitting parameters are needed to well describe the behavior of polylimited superconductors. So these fitting parameters are eta and epsilon that are included as corrections of the magnetization term, and also another correction of the size of the course. So we are happy to see that our model is able to describe our the dependence of the cerium coupled to silicon 2 along field. What we expect, or what the model is telling us, is that At low fields, we have vortex lines that are well separated to each other, but we can see that the contrast between the inside and the outside of the Planck line is actually really well defined. But since once we are increasing the field, this contrast is also increasing, as well as the vortex core sizes. So, as I mentioned before, we managed to fit to use our model to fit our data, not only the field dependence, but also the temperature dependence of the cerium coupled to silicon-2. And the important thing about this data, it's like there's a huge debate about what is the pairing symmetry of the superconducting gap of cerium coupled to silicon-2. So it has been proposed by previous heat capacity measurements that the superconductor maybe have a double S wave gap. So we tried our model using different gaps, a single S wave gap and a double S wave gap. And for our model, this double S wave gap works better than the S wave gap. So we are confident to say that we agree with the results previously found by heat capacity measurements. Since we don't want just to use this model, we want to use it in several polylimited superconductors. We also use it in cerium, cobalt, indium 5, using the D wave gap that it has been previously addressed. And we are really happy to see that, as in the case of cerium coupled to silicon-2, they are able to describe, and the model is also able to develop this peak just before arriving to the BC2 at several temperatures. You may notice that this drop on the form factor, it's not described by our model, but this has been intentionally not included because we think that this drop on the form factor is not because of polyparamagnetic effects. Then, following the trend of studying new, or studying other unconventional superconductors, we continued our research studying another really well-known high TC superconductor, which is IPCO. The particularity about IPCO, it's not only that it's high TC, it's also that the superconductivity is developed in two directions. We have a couple oxygen plane on the AB direction, which it has been reported, or it's thought that it develops the wave superconductivity, and also we have superconducting change of copper oxygen on the B direction, which it has been suggested that carries S wave superconductivity. When we combine these two contributions, we end up with the superconducting gap, which has either the S wave and the D wave contributions, and the nodes will move depending how strong this D wave superconductivity is on the sample, depending on the field that we are applying. So in the past, the form factor and the vortex lattice of IPCO has been studied up to 16 Tesla. It was first reported 3 different structural transitions, so having a low field transition and an intermediate field transition and a high field transition. These transitions are addressed, or we think that they are related to the anisotropy of the London penetration depth along the AB direction. However, we are happy to say that we were able to measure the vortex lattice and the form factor of IPCO up to 25.9 Tesla. This vortex lattice, this is the first time that the vortex lattice is saw with neutrons up to that field. And also it's important because we obtain this data using tough experiments and not monochromatic instruments. So as we see on the picture, the opening angle between two between the two Bragg reflections, it keeps increasing until it reaches a square structure. And once arriving to 25 Tesla, we see a plateau, and it's actually stabilizing at 100 degrees, which means that this is what we think is that this is not driven by the London penetration anisotropies, and this is because of the movement of the nodes when we are applying some field, a certain field. So since the superconductivity is controlled by the planes and the chains, we can also control these contributions by adding calcium to the sample. So once adding calcium to the sample, we are adding the concentration of holes into the superconductor, which means that the superconducting properties will be changed as well. So as in the case of IPCO, we were able to measure the vortex lattice on a 15% calcium doped IPCO sample up to 25 Tesla. However, on this 15 calcium doped IPCO sample, we were not able to observe any transition, and we thought that this is because of pinning effects. However, another experiment was done before the 15% calcium dope on a 4% calcium dope IPCO sample, and we see a similar transition between the intermediate phase transition and a high field transition, in which the behavior is actually the same, and also is arriving and also the structure is stabilizing at 100 degrees, but the whole diagram is shifted by a factor of 2. So we think that when adding this calcium concentration, and also, as I said, changing this whole concentration, we are actually changing the phase diagram, or we are actually changing the vortex lattice behavior along field. Last but not least, since we were able to measure the vortex lattice, we also were able to measure the form factor of the 4% and 15% of the calcium doped IPCO, and also on our IPCO sample. Starting from the IPCO sample, we see that the form factor is not actually decreasing it's not actually decreasing with field, and it's actually stabilizing at a constant value up to 25 Tesla, which can obviously, we mentioned in our paper that this cannot be well described by the London model expression. But apart from that, the 4% calcium dope shows a similar behavior and also cannot be addressed using the London model expression. But for the 15 calcium dope IPCO, we were able to fit this data using the London model expression. And we found out that apart this whole concentration of this calcium doping also affects to the BC2, because on the 15% calcium dope, we think that the BC2 is heavily decreased because of this calcium doping. So finishing this talk, so we found direct evidence of polyparamagnetic effects on cerium copper 2 silicon 2, and we successfully developed a model to describe the behavior of polylimited superconductors that not only works for cerium copper 2 silicon 2, but also works for cerium cobalt indium 5. And we aim to use these kind of models in all the not well-behaved superconductors. So we may be using, we may use this model to maybe describe possible polyparamagnetic effects on the IPCO sample. Also, we extended the range that the vortex lattice will measure up to 25 Tesla. And also we performed these high field measurements on a 15% calcium doped IPCO sample. And we found evidence that this change on the vortex lattice structure is because of the D plus S wave contribution on the superconducting gap. And since we are still interested of finding more unconventional superconductors that deviates from the London model expression, we also study other materials, such possible natural topological natural superconductors, and we may be using this kind of model in future poly-limited superconductors. So thank you very much.
Thank you very much, Emma. Yes, at this point we would have a short break here. Let's gather here again at 10:15 in more than 5 minutes. And then we gather again for the defense part.
But Lisa.
Sorry, I'm here. Here question.
No, I was just wondering how they get done. Where did they live now?
Did they arrive with car? It's the left.
I can also.
Yes. That was okay. Check the brightness.
I saw my sister sleeping.
I feel like some sort of train mapping or whatever.
Que para él es divertido hacer física, por eso él no sigue aquí. He said that he should keep going for 4 years. This is my sister.
Yes, so easy with this hybrid setting.
She's able to speak English, so she cannot pretend that she doesn't understand.
You came here yesterday from. Sorry? You came here yesterday?
Sorry, I just wanted to.
We are running out.
¿Todo bien?
Well, slightly worried that Sebastian can see the lectures in the audience.
Most of our group are all familiar with the X-ray infection.
Sorry, the
Same method.
Oh, yeah. Only as a consultant role. And in the end, it's going to work, but it's not. But that's a long-term project. Yeah. One of these things, and either will equal zero. That kind of thing.
I know I had like my foot in a cast. Yeah, get off.
So Sebastian, apparently I have to say hello for Martin, and apparently you need to shave.
Yeah.
Hi, Martin.
Yeah.
It's not for me.
Yeah, that's perfect. Nice seeing you.
Nice to see you, Martin.
That's also nice to see you, Martin. Right, I don't see you now, but
Yeah, he's on the back keeping the baby.
yeah.
It's absolutely amazing. These laser cooling is produced. When it first came, I thought, oh, well, this is just giving you a new set of elements. So instead of just helium being solid, you can now get sodium, you know, things like that. And then it's moved on from that so far. You can ways it.
I was understanding that the point where she starts to talk about
Yes.
experiments, so I'm not an expert. Stuff, I guess. You can call my knowledge. But yeah. Yeah, it's nice. I feel like we can do some experiments. Like our neutron CDI. Neutron Break CDI. One single. What is the coherence length of a neutron? It's a very difficult. But it's funny that they study big things. I thought they still go to these vortices. I mean, experiments, which are like atomic. It's also vortex, but it's like it's biological.
Even worse.
Oh, yes. You can freeze and polarize X-rays, and they interact with polarized
Exam is on Monday. And this re-exam last and then no, but it's a long question. It's just the 8th. So this boss.
I managed.
Yes. We had a okay. Very grand.
It's very nice.
Okay, so then it's the same. So he was just.
It is, yeah, yeah. You have to get there by train. I don't know what's going on there.
So that's what. They have. When
Welcome back, everyone. Good that you're still here and following the most exciting part now. And also back, and we have our committee here. So we are in place here to get started with the scientific discussion of the work. And of course, first will be the opponent, Milbauer. Please go ahead and start discussing with Emma. Start with your.
So I can just start or just go ahead or?
Yes, please just go
Okay,
ahead.
perfect. Because I don't see Emma anymore.
Right, you said, sorry, I will change back to her, but just go ahead.
Okay. So hi Emma. So thanks for the very nice talk. Be assured, I'm similarly nervous as you are. It's the first time I do this in Sweden, so okay, we'll see. We'll have a fun 45 minutes, a fun hour. So what question do you fear the most?
Happy, so.
Okay, so no wishes. Okay, so yeah, okay. So I was wondering. Okay, let's start with something easy. So you did lots of small language sketching. So can you let us know about why neutrons are useful to do that? What's the interaction of neutrons with matter?
Could you please repeat the question?
Sorry, say again.
Could you please repeat the question?
Okay, sorry. So you did lots of small language sketching with neutrons. So why do you do that with neutrons? Why neutrons are useful to do that?
Okay, fair enough. So neutrons are used because they carry a magnetic moment. So to be able to see magnetic structures or magnetic arrangements of materials, we need the neutrons to interact with these magnetic structures. So if we don't have the magnetic moment, then we will not be able to see anything.
And so what else happens when you send your neutron beam to your samples? There's of course an interaction which is not magnetic.
It may happen because we can also see, I mean, they also behave as other kind of scatterings. We can also see the atomic structure of the material, not only the magnetic one.
Okay, do you really see the atomic structure on small angle scattering?
So that depends on the wavelength that we are actually using, and also if we are out of the superconducting behavior.
Okay. What else do you see in your background apart from
so
structure?
We can see what we call spurion effects, depends on the sample as well. We can observe scattering from the background, and then we can obviously we can see the unscattered neutrons, so that's why we need a beam stop.
Okay.
And we need to blind some of that unscattered neutrons.
Okay, yeah, you need to catch these, otherwise they just burn a hole into your detector. Okay, perfectly. So let's talk about your experiments. So what you do is, as you said, is a diffraction experiment on a vortex lattice, and you've done that also on TOF instruments. So what kind of analysis can you do when you have your diffraction data? What kind of data you can extract from looking at your peaks?
So first of all, we don't see the peaks directly when we make a measurement.
Okay, well, let's talk about monochromatic. It's easier to talk about monochromatic.
Right now. So even in the monochromatic case, we have to first measure the scattering under certain conditions of temperature and field in the superconducting state. That's what we call the foreground. And also we have to measure the scattering out from this out of the superconducting phase. And that's what we call the background. And then we will subtract the foreground from the background, and then we will end up with our signal. So in our signal, we will be observing the actual Bragg reflections coming out from the vortex lattice on the superconducting phase.
Okay, so what do we extract when you now have a
what we extract is the integrated intensity for every single reflection that we observe.
Okay, what else can you extract?
So depending on the arrangement of the Bragg reflections, we can also obtain the anisotropy of the vortex lattice, or what we usually know the opening angle between Bragg reflections.
Okie dokie. What else can you be looking at? So, for example, the peak shape. What does the peak shape tell you?
Oh, fair enough. So ideally, the peak shape should be a delta function, but that's not going to happen because of the limitations of the instrument and also on the perfection of the sample. So the peak shape, or what we usually call the rocking curve, it can be approximated by a Gaussian or a Lorentzian factor. And it depends on the material that we are using. There's no specific choosing of function.
Okay, and so what does the peak shape tell you, and the width of the peak? If you, let's say, smear it from resolution.
So it tells you about the resolution, the wavelength spread that we are using on the instrument. Also, it tells us about the perfection. So when we have a good sample, we will have really fine or really thin rocking curves on our sample. Also, it will tell us about the background that our background subtraction was good or not. What else?
Well, I'm looking for a specific term. What happens if you Fourier transform your rocking scan? What does this give you? This is a specific length. When you look at your vortex lattice, if you have your rocking scan and then you do a Fourier transform of your rocking scan of your width. This is if you think about correlation. Well, let's ask the question differently. So for doing such an experiment, you require a coherent beam. So what defines your beam coherence on a SANS experiment?
You mean the spread of the wavelength?
That's for example, that's one point. But in general, they're like, if you consider your Bragg peak, and they're like different directions in reciprocal space, being like in the direction of the momentum transfer Q, or like perpendicular if you go a rocking scan. And so what is defining your coherence of your neutron beam? How do you make sure that your beam is coherent? This is think about the instrumental resolution. What is the definition of the instrumental? What influence do you have on the instrumental resolution on SANS?
So usually the instrumental resolution is made, it's given by the spread of the wavelength. So
that's perfect. That's correct. What else?
Also depends on the distance that we are using.
Perfect. Yeah, this is the collimation distance and your slits. What else do you have? Does the detector resolution play a big role?
Like the pixel size.
Pixel size, exactly. Okay. So now what happens if you extract from the rocking curve, you can extract the correlation length, which gives you the way, or which gives you a measure how well ordered your vortex lattice is along the beam direction. Can you estimate how long what kind of values do you get for this correlation length?
Like the d spacing of the lattice in real space.
Well, this would be the correlation length in perpendicular directions, so along Q. So if you have your rocking curve, and then you look at the rocking curve widths and saying, yeah, this corresponds to, I don't know, so and so many angstroms or nanometers of order along the field. How well ordered is your vortex lattice along the field? Do you have an idea? Or can you estimate from the rocking widths? And what would you need to do if you have a rocking curve, and then you would need to calculate the correlation lengths along the beam? Let's say I give you a rocking curve, and then you can.
I think so that would be the QZ, the QZ distance. So usually bright reflection is usually found in some specific position in the physical space. So once we rock over sample, we want to know the width of this bright reflection along QZ direction.
And so, what does the width tell you? If you see a width of I don't know, tenths of a degree in a rocking scan, how can you compute the correlation lengths along the field? What do you need to do? Well, let's ask the question completely differently. Maybe it's easier if you do it like this. So if you check the textbooks on small length sketching, and then you go for the coherence volume of the beam, and then you'll find the expression saying, the coherence volume of the beam is given by lambda squared over delta lambda. For SANS, and so the delta lambda over lambda, I guess that's what you know from your velocity selectors. I don't know, typical value is 10%. Yes. For the wavelength spread. And so if you put that into the formulas, and it's just lambda squared over delta lambda, and then you end up with a correlation length along the beam of 10 nanometers, which is 100 angstroms. Yeah. Does this sound useful for your vortex lattice? what is the correlation length you observe in your experiments?
So I'm sorry, I'm just thinking about the Q spacing of the vortex lattice of the rock reflections on reciprocal space.
Yeah, maybe it helps if I do a sketch. Can you see that if I sketch something, does it work? You see that whiteboard, or is it, or don't you see that? So let's say this is our direct beam. You see that? Yeah, perfect. Okay, great. So then we do have a KI here. We do have a Q vector, and then we have KF. And then we have our detector here. And then we do a rocking scan. So we have the sample. We rotate here, and then we have a Bragg spot here, and we look at that one, and then this one. And then what you'll get is the rocking curve, which looks like this. And then you extract this length by fitting your rocking scan. And if you look in Q space, this is essentially we're doing that scan. So we have the Ewald sphere somewhere here, and then we move our Bragg our lattice going through the Ewald sphere here, and then we extract the correlation lengths along the field. So this is also parallel to this is the field direction here, which is parallel. And so if you extract that, you'll get correlation lengths of many hundred nanometers. And I was just wondering if you check the textbooks for small length sketching, where you have the correlation lengths along the beam. So let's say, okay, this is the Z direction. And then you say, okay, the correlation length along Z, this is lambda squared over delta lambda, which is like around 10 nanometers. And this does not correspond at all to the very long correlation lengths you can extract from your experiments, and that's real, of course. So I was wondering if we can work out why this is the case.
I mean, I know about the importance about it, because it can tell us if the measurement is actually limited by the instrumental resolution, or if it's actually the real signal that we are observing.
Exactly. Yeah, this is right, but doesn't tell you why you measure a correlation length that is much larger than the coherence of your instrument. That should not be possible.
All right.
Anyway, okay. Maybe we'll come. Maybe we'll come to that later. Maybe that's a rather neutron question. Okay. I will stop sharing that. So we'll do something else. Maybe we can discuss that later. So then I was wondering. So you're looking at symmetries of vortex lattices. So maybe you can give me a brief overview of the different influences on symmetry of vortex lattices. If you say, okay, well, I have some deviation of a 6-fold vortex lattice. So what can be the cause for that?
Strong deviations from regular from isotropic structures.
Exactly. So what are typical causes, and then you can we can think, okay, what's the for different materials, what's a typical cause? What would be the field dependence of that? What would be the temperature dependence? So just a small overview of like different sources of anisotropy for vortex lattices.
So there are several, as you mentioned, there are several reasons that we can deform or we can observe an anisotropic vortex lattice structure. One of the causes would be, for example, rotating our sample with respect to the magnetic field. And we will see some anisotropy or elongation of the structure of the sample in one certain direction. Then also we have, as in the case that we observed on IPCO, that the structure it may be changing along field due to anisotropies of the penetration depth along a certain direction, or it can be caused because of the movement of the nodes that we mentioned before. So, yeah.
Okay, so what about the gap symmetry? Can you do a direct one-to-one of let's say correlation of gap symmetry and then vortex lattice symmetry, or is this not possible?
Depends on the material, but usually we have two main arrangements, which is a triangular lattice or a square lattice. And so usually S-wave superconductors show a triangular arrangement, meanwhile D-wave superconductors usually show a square arrangement of the vortex lattice.
Okay, great. So then let me have a look on my list of questions. So you also did use the bias theorem for your analysis, for your data analysis, and you didn't cover that in your presentation, I guess mostly to time reasons. So can you very briefly summarize? Okay, what's the fundamental basics of this bias analysis?
So first of all, the SOA, it wasn't developed by me, it was developed by one of our collaborators, Dr. Alex Holmes. And basically the reason of using Bayesian analysis to better visualize vortex lattices is as we mentioned before, we have a lot of noise, or when rocking a sample, depending on the rocking direction that we are using, a specific rock reflection can be rocked much more times rather than the rest, and then the intensity is not going to be completely homogeneous for the whole vortex lattice. Now the reason is that we wanted to include weights depending on the areas that we expect the vortex lattice reflection. Because if we use the conventional way of measuring reflections, we have the same importance for all the areas. So using this analysis, it specifically chooses where we expect this vortex lattice line to appear. And also by using this Bayesian analysis, we can blind those areas that are not from our interest. So then we will just see the signal that is coming from the vortex lattice.
So what you're using as a price, the information that the Bragg peak is a Bragg peak, of course, and then it rocks. So would it be possible as a let's say extension or add-on of that, not only to use the information that that it rocks, but so to say use the information that the vortex lattice needs to have Bravais properties?
Excuse me?
So would it be possible to extend that bias model that in a way to have as a prior that the vortex lattice has Bravais properties?
That's what I tried to extend a little bit in my thesis. It was not only visualizing the vortex lattices, but also subtract the form factor using this Bayesian analysis.
I was more talking about that the bias exploits the fact that this is a crystal lattice. So there's okay, if I have a peak here, I need to have a peak here just on let's say just due to symmetry reasons. Would that be a good idea to do that?
Just with one single peak.
No, but if you would just exploit the fact that it's a lattice with crystal symmetry. So if I see a peak on let's say if I see a peak on one side, and if this is a lattice with Bravais properties, there needs to be a peak on the other side as well, for example. And I guess this would be nice to include it, I guess.
I think in theory it should be possible, of course, but you still need the priors as the raw data and also good rocking curves well defined on the signal that we are observing. So it's an interesting question.
Maybe it's also a question to Alex. Okay, then let's have a look at the heavy fermion compound. So this cerium copper to silicon 2. A very stupid question because I mostly work on classical niobium materials. What do you think is the parent mechanism in cerium copper to silicon 2?
Oh, how is it arised?
What's the pairing mechanism? What's the pairing mechanism of your heavy fermion Cooper pairs in that material? What is your guess? I know this is a very unscientific question.
Could you please rephrase it, please?
So what for classical BCS you have phonons.
Oh, yeah.
You're binding your Cooper pair.
Meanwhile, in
What
this
happens in cerium copper to silicon 2? What's your guess?
So basically, the phonon electron interaction is not happening anymore. So the interaction changes completely, and also it's because of the heavy fermions that are creating this superconductivity.
Yeah, but so what binds your Cooper? What binds your heavy electrons or electrons to a Cooper pair in that material instead of phonons? There needs to be something. What is your guess? You need some way of mediating your
spin interaction. I'm sorry. It's usually mediated by a spin interaction.
Spin interaction. Okay. So maybe you can explain me so a heavy fermion, that's a system where the electrons are heavy. And you speak a lot about Fermi liquid behavior and the non-Fermi liquid behavior in your thesis. So what is a Fermi liquid? And how do you come from a Fermi gas, so the free electron gas, to a Fermi liquid?
So usually the way that Fermi liquids are addressed in certain materials is because physical properties, they do not behave as normal metals. So you have a change on the dependence of the heat capacity and also in the resistance of the material and on the magnetic susceptibility.
Okay, so what kind of characterization does a material need to have to fall into the heavy fermion? So that it's a heavy fermion.
Usually the mass of the particle, the effective mass of the particle is much heavier than a conventional electron.
Okay, so this is that. So the electrons are heavy. That's why it's called heavy fermion now. Okay, so so in a regular, let's say in a regular metal, you have a Fermi gas of electrons. And so how do you get from a regular metal to like say with a Fermi gas to a heavy fermion? What do you need to put in as a physical ingredient to have a heavy fermion system?
So in particular with heavy fermions, the electrons that are involved are F electrons.
So what is the fundamental principle of heavy fermions? If you start, let's say we start with a Fermi gas, free electron gas, and then we have our electrons, and then what happens to go towards a heavy fermion? What is the difference of a free electron gas and the heavy fermion? Why are the electrons so heavy? Or seem so heavy? So heavy. Yeah, I think you have it somewhere in your thesis. You did a very nice introduction into heavy fermions. Think about the Kondo effect.
So the first thing that comes up to my mind is thinking about the differences in orders of magnitude apart from the effective mass on the Sommerfeld coefficient.
Exactly. So the electrons are super heavy in heavy fermions. But just the question is why? Why do they have this huge electron mass? But let's say like this. What is the if you take a free electron gas, so Fermi gas? What do the electrons not do?
Well, they tend to not interact so much.
Exactly, they don't interact. And so what happens if you go towards a heavy fermion?
So I mean, the particularity is that they have a big interaction between the.
Exactly, that's the key. And so what is the trick then to make it like straightforward and easy for us to? So you don't want to mess with a many body problem or so. What is the trick of heavy fermion theory? What do you do with all these interactions? Because you're not able to look at a single electron anymore in a heavy fermion. You have like a electron and a dressing cloud of electrons, and this is messy and complicated. But what's the trick? What we do to make this look like a heavy fermion? It's like a fermion, but it's heavy. So what's the trick? What does one do with all these interactions? You almost said it. You're very, very close.
I think the only thing that comes to my mind is the energy scales has to be changed.
Exactly. So it's all renormalized into the mass. So all these interactions are renormalized into the mass, and then you can treat it as a Fermi gas, but heavy. Okie dokie. Then maybe you can. You don't have slides around. Okay, so let's talk about the your stay with the serum copper to silicon 2 and your Pauli paramagnetic effect. So if I understood this correctly, what you get is maybe we can look at page 44 in your thesis, where you show the London contribution in the top half and the Pauli paramagnetic contribution in the bottom half. Yeah, exactly this one. This very nice blue picture. So if I understood your thesis correctly, you start to see a signal in the neutrons from your vortex, which is the London contribution, and then in the core of your vortex you have like paramagnetic spins having getting a paramagnetic polarization or some polarization. This gives it rise to an additional signal. And of course, for me as a neutron sketcher, this would be highly interesting to separate these contributions. I don't know what could we think of how this could be separated. Is there a way, or what could we do to say, this is the paramagnetic part and this is the London contribution?
Depending on the spin direction, when we have paramagnetism, the energy, depending on the direction of the Ampere spins, change the energy levels and also increase the mobilization of the vortex cores.
So what kind of, I don't know, can one do some kind of, is there some magnetostriction maybe around, which would give you some signal from your paramagnetic spins? I don't think this is the case. I don't know. Would it be possible to use inelastic neutrons to distinguish between the London part and the paramagnetic part?
To be honest, I've never thought about it.
Would both be elastic?
Excuse me?
Would both signals be elastic?
Yeah, but on figure 311, it's just a simulation.
That's absolutely clear. But so would your signal from the London part, would it be elastic?
So I mean, we have the elastic scattering.
Would be elastic. So would your part from the paramagnetic, would this be elastic, or would this have a finite line width? If it's paramagnetic scattering. Which is essentially fluctuating, isn't it? If it's paramagnetic.
I don't really understand the question.
So if you consider a paramagnet, just not a ferromagnet, but a paramagnet, would you and you do an experiment with neutrons, what would you see? For a ferromagnet, it's easy. You get a ferromagnetic Bragg peak, which is static. If you do paramagnet, if you increase the temperature, okay, let's say like this: you do a diffraction experiment on a ferromagnet, and you observe a ferromagnetic Bragg peak. Very simple diffraction experiment, and then you increase the temperature and you go towards the transition. What do you see instead of the Bragg peak? At the close to the phase transition or at the phase transition? Say if it's a second order phase transition.
It's just like looking.
What happens close to a second order phase transition? Forget all neutrons. Let's just look at the second order phase transition. What do you see there?
I mean, second order transition, we usually see a smooth change instead of a drop as on the first order transition.
Yeah, that's right. And what else do you see? Very, very broad.
I would rather say diffuse scattering.
Yes, you see diffuse scattering, you're right. And that diffuse scattering comes from?
From short range correlations, maybe?
Yeah, fluctuations. I say fluctuations. It's fluctuations. And so the fluctuations do have a finite energy. Finite energy widths, and I was wondering if you would if your Pauli paramagnetic scattering, if it would be possible to measure the line widths of that one, because it's in principle it should be not static, it should be fluctuating. I bet you would need a very, very good energy resolution to look at this, but it might be impossible to do that just because of the width of the energy. But I think why not think about this and maybe think about this if this would be possible to do that. Let's have a look at the second one. I'm just looking for another question. Okie dokie. So then let's have a look at the YBCO what you did. And so you did measurements at XZ at Berlin with a very high field. I think 25 up to 25 Tesla. And so you did this on a TOF instrument. So what is the fundamental difference on if you do TOF and monochromatic suns?
You don't have velocity selectors touching from that.
Okay.
Because you have to use several wavelengths at the same time. And the other difference is because of this, because you cannot choose a single wavelength, instead of rocking our sample, the wavelength will be the ones selecting different energies, so and passing through their Bragg reflection. So it would not be needed to rock our sample.
So you don't need to rock. Well, how does the resolution compare if you do a monochromatic experiment or a TOF experiment? in a rocking scan, what gives you the better resolution?
Not particularly, because you, as I mentioned, we have wavelengths working on. So, but we have a wider range of energies.
So which instrument would you prefer, monochromatic or TOF?
Absolutely monochromatic.
Don't tell that to the ESS guys.
I'm sorry.
Yeah, no, you don't need to be sorry.
Also, the analysis process is rather more simple in monochromatic instruments.
It is much more suitable for single crystal diffraction. I totally agree. It's like you see what you get, and for the TOF you don't see what you get. You have to do some mathematics to see what you get. So what do you think concerning looking at the form factor of YVCO? Until which field? This is just a guess question. Until which field would you think is possible to observe a break peak at ESS? If you say, okay, ESS has much more intensity than Berlin, what kind of magnet do we have to build? 40 Tesla, 50 Tesla?
Depends on if they have buildings available for the cooling system of the magnet. So.
That's your homework, Alex. So what would be desirable concerning science? So you did lots of high field stuff. What magnet would you like to have? What do you think is useful?
That's a tricky question, because I mean all science is always useful. If I could choose, of course, I would like to explore ECO up to 50 Tesla, which has been studied using pulsed magnetic fields. But I don't know if it's going to happen on the ESS.
No, maybe not. Not in the next years, I guess. But this is this still small angle sketching? When you like 50, if you have 50 Tesla, what's the break angle? It must be like huge. Well, it depends, of course, the wavelengths.
That's good. You will need a huge detector as well. I don't know if it would be possible to go farther than 20. I mean, it's always possible to go farther than 25 Tesla, but then it requires also a new size of the detector. Also, we are limited by the distance that is able to reach the sun's instrument.
Well, you need to get it out of the magnet, I guess. This might be your primary problem, because your magnet has some opening angles and you need to get it out of your magnet. If your break peak will be absorbed in the magnet, you will not be able to see it. How are neutrons detected, by the way?
Excuse me?
How are neutrons detected?
So on a TOF instrument or in a monochromatic?
Depends on you.
Well, usually they are detected by position detector. On a monochromatic instrument, it is just the number of meters that you have detected for certain pixels. Meanwhile, the monochromatic depends on the time that you arrive to a certain detector. So,
do you know what kind of detector, what kind of detection principle is used for neutrons? Neutral particle that's not easy to detect. It's something like no, it's not this. It's this one here. Can you just put a counting tube for a neutron?
Could you please repeat it?
How can you just put a counting tube there and count a neutron? How does it work? It's neutral, so how do you detect a neutron?
So the detectors usually have helium. So
what kind of helium? The cheap or the expensive one? It's the expensive one. It's the helium-3, of course. Okay, what you need to do is you need some neutron capture reaction, and then this will capture the neutron, and then you out of this reaction you get the charged particles, which you can then detect in a counting tube, for example, or you can use a scintillator detector. But you always need some kind of conversion to get the neutrons converted into something what you actually can detect. Okie dokie. I guess my hour is close to being over. Maybe I have a final question. That's a question where I don't know the answers, because I mostly do niobium and simple materials because I'm a neutron guy. There's this big fuss about topological superconductors. And can you give me a neutron scatterer's introduction in why is there such a fuss about topological superconductors, and so explain it in a way that I understand it, because I have no idea about that.
first of all, I must say that I'm not completely expert. That's why I try to give a wide explanation at the beginning of the chapter. But basically, for me, the particularity about these superconductors are they are able to show the peak wave superconductivity and how they are managed and the surface properties that may show. I know that can be used for qubit technologies or in quantum in superconducting. In quantum computers, but again, I'm not an expert. The thing is like the key property why everyone is so behind this superconductor is that at the moment there's not a topological superconductor, a natural topological superconductor that has been addressed. It has been always observed by the interaction in conjunction with another material.
So it means you have like some artificial layer structure where you have a superconducting surface and some I don't know, not conducting or bulk. So but if you would have a natural topological superconductor where only the surface would be superconducting, would this be useful for a neutron experiment? Would the neutrons see something, because it's neutrons is like really a bulk technique, or would you do, or would this be what could be done?
That's a good question. Since I mean, in neutrons we mainly use bulk samples to observe. I cannot say that nothing can be observed, that when we have 2D materials are particularly difficult to manipulate on neutron experiments.
You could try grazing incidents, but I'm not sure if you want to do that. Grazing incidents, small length sketching also might be a thing to look at some in-plane correlations of that systems, but I'm not sure if this has been done or if it's possible at all. it's a notoriously intensity limited technique. Okay, so I'm at the almost at the end of my questions. I've got the very last one, but a very simple one. You mentioned the Harry Ball theorem. I have to ask about the Harry Ball theorem. Can you briefly explain the Harry Ball theorem and why this is relevant for vortices? And then I'm done with my questions.
Okay, I've read a little bit about it since I had to. So the Harry Ball theory, it says that the arrangement of the vortex lattice can change depending on the direction that you are applying your magnetic field with respect to the crystallographic structure of the material.
Why is it called Harry Ball theorem?
Because you can never.
Well, imagine a Harry Ball, a mathematical Harry Ball, and take a comb and try to comb it. What happens?
So, in the Harry Ball theory, it says that all the sphere can be ordered in some way except for the poles at some point.
So this translates to the Harry Ball. If you have a Harry Ball and comb it, you have 2 points where you have non-linearity or so. Or the poles, for example. And so you have like two. What do you have if you have your Harry Ball and you try to comb it?
I mean, if I try to comb it, it's what I said. It's like in the poles, you will never have a completely order except for the upper and the down poles.
What do you get on the poles? What's that? What could happen on the poles?
You get it's not nodes. You cannot. You get singularities.
Singularities, yeah. You can have whirls or like these like a tip or and a bald spot. Okay, perfect, great. So I'm done with my questions. So
all right. Thank you very much. Thank you, Sebastian. Thank you, Emma, for this in-depth discussion that we had here. See here the technique. Right. Then it's time now to go to the next step, which is questions by the members of the examination committee. I would suggest that we stay on Zoom for beginning, and that we start with Christine Sassa to ask questions. So I will switch back that you can see. Right, so please go ahead.
Thank you very much. How are you, Emma? How are you holding up?
Sorry for asking so stupid questions, Emma. You're doing fine.
I agree. But just brief, relax. I mean, it's your show today, so enjoy it. This is a good conversation that you should have. So don't be stressed and don't be scared. All right. So, but I have to say that thank you for the thesis. I really enjoy reading it. As Sebastian said, I really learn a lot. Also, I'm not a science expert, so for me it was also very good. And I apologize in advance. I will maybe ask you super basic questions sometimes, and yeah, and if it is, sorry for that. So my first question is regarding one equation that you have in your thesis. Is the equation 2.13 about the Brandt equation. And there you detail that actually there is a constant that is called C, and you say that this value is typically between one quarter and 2. Can you explain a little bit further what is the meaning of this constant and why it's comprised between this value?
Okay. Thank you for asking that. So basically, as I mentioned in my talk, we need this Gaussian cutoff to precisely define the finite size of the course and to have this exponential decay with increasing field. So the reason by choosing those values, so that depends on the material that we are actually using. But the paper that we have just published a couple of days ago, we proved that the actual value that can be used for several materials is 0.44. And as we mentioned in our paper, that value matches quite nicely to the exact solutions of the Ginzburg-Landau equations. So is let's say that we use those values as to be a good approximation to the exact solutions for the Ginzburg-Landau equations.
All right. Okay. Thank you very much for this this explanation. Now I have also another question regarding a statement that you make in page. Sorry, now I need to find my page 18. So you said that the rocking curve is usually fitted to either a Lorentzian or a Gaussian function. And I mean, I have quite a simple mind, but for me, I will actually use a combination of it because the Gaussian would capture what is actually the experimental resolution, and more or less the physics will be the Lorentzian. So how can you explain me a little bit more in details how do you more or less choose this? I mean, the fitting function is just because you look at the curve, or is it something else, or do you combine? Can you detail that for me, please?
I completely agree with you, and that's an excellent point. So ideally, we rather should use a Lorentzian, a convolution of the Lorentzian and the Gaussian, because the Gaussian will be able to describe the peak behavior, and the Gaussian will be much more adequate to record or to express the shape of the background of our signal. I would say that we only stick to one just to simplify the data analysis, and the differences between using convolution and rather just a Lorentzian or Gaussian is not such a big difference, and usually lies inside the error bars of our fittings. And the reason of choosing one or another, I briefly mentioned it before, it depends on the system that we are working with or the background that we have for any specific system. So yeah, that's all.
Okay, I see. So ideally, you would like to do a combination of both. Yeah. Okay. Yeah, I see. Now I have another question about the Bayesian analysis that you perform on SONS data. As I understood it, it allows you to get a better overview of the vortex lattices, right? Mm-hmm. But as I understood also, you're smoothing the data after doing this analysis. And I was wondering, what is the smoothing procedure you're using in that case? And how do you think that impacts actually the data in itself and maybe also the interpretation of the data? Can you comment on that?
So, as you mentioned, all the pictures that I usually show on the thesis are either smooth using GRASS or is all smooth using this Bayesian analysis. But that when we say the word smoothing, it only affects to the visualization of the vortex lattice. It doesn't affect to the actual data or the actual rocking curve that we are looking at.
Okay, but what is the smoothing function? Because that doesn't tell me. You say you use a program, but what is because there is different way of smoothing. And I was wondering, what do you use, even if it's to make a more pretty image, as I understood it. And I mean, believe me, I know what is pretty image. I'm for Amarpes, so we like pretty picture. so this is why I was wondering a little bit more about that.
So we usually use a Gaussian smoothing.
Okay.
Depending of how much we want to trick our pictures, we use a 3-pixel Gaussian or a 5-pixel Gaussian.
Okay. Still connected to the Bayesian method, can you explain me a little bit more? Because now in your thesis, I saw a lot of nice thing about it, and I'm quite convinced that this is the way of going and all. But I mean, all methods has limitations, right? What are the main limitations that you can say about this method, and what would you do to, let's say, try to avoid this and to make it better in that sense?
Thank you for asking that. So actually we found several limitations. So just remarking that all the data rocking curves and form factor that I show in my thesis are obtained from the classical method that I described, from the rocking curves and everything. And I didn't apply any Bayesian procedure to obtain the form factor in either of my papers. So the limitations are usually when we have a vortex lattice, or we detect the Bragg reflections of the vortex lattice, sometimes we will end up with samples that we cannot observe a rocking curve. We may be able to observe the vortex lattice itself, and I think it's an excellent example on page 26 of the case of the beta dismethylhelium. We can see some of the spots. We can see the lateral ring coming from the vortex lattice, but on that specific experiment, we couldn't rock and we couldn't detect rocking curves from the specific Bragg reflections. When implementing this data on our Bayesian analysis, it's unable to improve it or to obtain any physical quantity. So that's, I would say, the main disadvantage.
I see. All right. Now, Maurice, coming to the result about the heavy fermions, I find them very interesting. Actually, I really like them, and I would like to have a focus on the figure 3.7, where you have on the right panel your data on the cerium copper silicon 2 and in comparison cerium cobalt indium 5. Actually, one thing that I was looking is at the scales, the ordinate scale, and I saw that there is kind of a 2 order of magnitude difference. Can you comment on that?
Yes, this is because in the basis, so at the beginning we thought that the scale should be the same for both materials because they are both serum based and everything, but at the end, when reinterpreting our data, we found that it doesn't, and they have different length scales. And so once we reported the London penetration depth on cerium copper silicon 2, we found out that it was much bigger than the London penetration depth found out on cerium cobalt 55, and as a consequence, that changes the length, the orders of magnitude of the form factor detected.
I see. Okay. Okay, that's explain. Yeah, I didn't think like that. Yeah. Okay. Yeah, that's a good point. And one curiosity is that I saw that the data start at 0.5 Tesla. Is there any reason why you? Now you're smiling, so I think I don't have to finish my question.
So it's actually related to what Sebastian asked me, like which field I should use, whatever. So depending on the instrument. So I on the real space, when we increase the magnetic field, we increase the number of Planck lines, and our d-spacing will be reduced. So when we go to the reciprocal space, that would be completely the opposite. So if we reduce the field, the Q spacing will be also reduced. So you will end up that your flux lattice line will be where your beanstalk is. So you will not be able to see that. Or if you can see it, it would be extremely noisy and noisy, and you can barely see the signal. Indeed, we have data at 0.4, but it's not possible to obtain any information from that data.
I see. Okay. Still regarding the data on the cerium copper indium 5, actually you refer, I think in page 48, about the suppression of the form factor that is due to the actually FFLO state, which is kind of a very interesting, state in that sense, especially when you have also, if you compare it with cerium cobalt indium 5. Can you explain a little bit why would you expect and why would you get this suppression when you enter that state exactly?
Why do we expect it? Well, it has been mainly theorized that polyimide superconductors are the excellent materials to find out once close to the BC2. What you will be observing is an homogeneous superconductivity happening, and what's our thought that it may be the case in these materials is because we see this sudden drop that that sudden drop close to BC2 instead of a decrease much more smoother, and that has been previously calculated on a paper where you can see this reaches the maximum point as we see in the data, and then with a sudden drop.
Because also the thing with the existence of this FFLO state is really highly debated. And also for cerium cobalt indium 5. And actually for cerium cobalt indium 5, if I recall correctly, is that there is also competition with the spin density weight ordering there. How do you think this result of cerium cobalt indium 5 relate also to your sample on the cerium copper silicon 2? Do you think you can have a unified picture there or not at all?
Could you please repeat that last sentence, please?
Do you think you can have a unified picture? Because, both of heavy ferment compounds and, at the end, what we want is to try to understand what's going on in all these guys and why, and what is the generic phase diagram. And this is one of the, let's say, main thing we try to understand in our research field. So what are your thoughts there? If you have, so if I start again, so in cerium cobalt indium 5, as I say, you have the spin density width that's more or less compete with this FFLO state. At least it has been said that in some papers. Now, how do you relate this result to your compound?
Okay, we have some antiferromagnetic spin fluctuations, but that's more related to the superconductivity part rather than the FFLO part. And we assume this because of the similarities on cerium cobalt indium 5, and also because it has been reported that in that area by NMR studies that there's actually something happening that it could be related to FFLO, and these results are in accordance to what is supposed to be the first FFLO observed in an organic superconductor. So that's why.
So the next step will be try to looking in organic superconductor if they are big enough. Maybe. Okay. Also another question still connected with this compound is that, so from the data you can deduce both a single gap and two gap models, if I understood it properly. It was interesting that earlier in your thesis you mentioned in the intro some other techniques that, like for example, muon spin rotation, that you can also actually via this method deduce the gap symmetry indirectly. Is it what you have found, is it comparable to what has been reported by Muir on this kind of compound, or not at all?
I cannot say not at all, but it's true that for a specific case of serum silicon-2, you can have, at least when I was writing my thesis, like 6 different papers saying different pairing symmetries for the serum silicon-2. I don't particularly remember the case for the MUSA, but you have these specific heat measurements saying S+S. You have also another paper claiming that it's D+D, or like a mixture between the two by another SCM paper found. So yeah, we cannot say a hard answer what the pairing system could be for the serum difficulty.
What do you think would be a good technique to look at that, about the symmetry of the gap? If you have the temperature required and all.
Just because you can visualize the Fermi surface or pockets, but again, I'm not an expert, but I would like to know, maybe ARPES could be like interesting, but I have been told that it's quite complicated to perform on serum frequency.
Well, it's very complicated also for the temperature range, because their neutrons are much better. They can go very low in temperature, while in ARPES we are very limited, even though there is some progress. But yeah, you're right. That could be a technique to look at it. There is another, actually, I think with STM you could do that. But I am not aware about the studies there. So maybe you know more about that.
Well, we took as a reference also another STM, but they also have these proposed of multi-gap effects on the superconductor, but they claim something. I mean, they don't make a hard statement about which gaps should be, or the values of the gaps should be.
But there also one can, you can be critical, saying that, okay, these techniques like ARPES or SCM, they are surface techniques, while neutrons, your bulk technique. So you see the real thing, and we just see the surface. That's also another thing that you could maybe think about. And this is why there can be also discrepancy between this type of techniques.
Yeah. Yeah.
One can maybe imagine that. Then let's move to IPCO, yttrium barium copper oxide. I like this compound. I mean, he has been there since a lot, and a lot of things has been done, but still we are working on it, and it's still a lot of things to understand and found. Just let me 1 minute to find my questions. So I think it was very interesting that you put it, that IPCO is actually a both S and D wave superconductor. S wave because of the chain, and D wave because of the copper oxide plane, if I understood it properly. And that somehow it's connected, that's more or less have an influence on the vortice lattices, right? And I was just wondering, because now you took a very specific compound with IPCO that has this chains that runs and that can be ordered, and that then you have different phase and different TC and everything. How does that compare your result with some, let's say, single layer like lanthanum strontium copper oxide, that that it's kind of clearly a D wave? How do you compare your result in that case with some other cuprates family, when that the order parameter is very strictly defined there?
Well, in our case, we are confident to say about this nodes movement or about the gap symmetry, because apart that it has been previously reported, we have this angle resolved measurements, and they were performed at zero field, in which they have this deformed, well, not deformed, this anisotropic superconducting gap, which has these two, that the explanation, or the clear explanation from the paper, is that you need both contributions to end up with that gap symmetry.
But in the study you're referring, what was the technique they used?
And also,
Photo emission.
yeah.
In that case, I can understand, because with HARPES, what you will see is that you do the surface, and for this technique, you need to cleave. And IPCO doesn't have a natural cleaving plane, so in that sense, you will have copper oxygen chains most of the time. So then you have a mixed between the two, between the copper oxygen plane and the chains. And there's the HARPES data are very difficult to disentangle sometimes. And also another issue there is with IPCO is that you always end up with the overdope regime, and you never manage to really, it's difficult to go to the underdope. So you have to find tricks. So I can imagine that they found that, but from, let's say, bulk point of view, I was quite surprised to see that you can have S and D, because I always thought that what we say that it's like a S contribution is really mainly because of the surface. And I mean, for me, I would say that the neutrons don't see so much the surface. You see what I mean? So do you have a comment on that? Or
I mean, well, it's obvious that we can resolve part of the contribution from the A because of this. I mean, we could resolve, or we could see that we have this anisotropy on the London penetration depth, and also we could see an hexagonal structure called low. It has been observed, this hexagonal structure at low fields and intermediate, and also in intermediate field structure. So they are both. I mean, as far as I can know, I can just say they are both important. They can be tuned with the calcium doping, and they can be controlled depending on the field that we are applying.
okay. A question regarding the calcium doping of this compound. So you substitute more or less the yttrium atom by calcium, and more or less you end up with an underdoped sample, if I may say it, because the TC is then 57 Kelvin, right? The TC is at 57 Kelvin, as I understood from your thesis. And I was wondering, how do you think, I mean, 57 Kelvin for me remind me some specific IPCO sample without calcium doping that is typically around this ortho-2 samples, let's say, that has this type of TC. And I was wondering, do you think that when you put calcium, you actually introduce hole in your samples? And what I was wondering is that, do you think that the ordering of this hole can make an effect on your result and can impact?
In which sense? So
in which sense is that, so if you take the normal IPCO and that you look at the chains only, so now you don't have a calcium doping. You know that sometimes if you have the chains and that you have a specific order, you have specific phase on it. And I was wondering already there with neutrons, if the result can be different if you measure on the IPCO, let's say ortho-2, that has a similar TC than your calcium dope, and another IPCO sample that has no ordering on the chain, so that they are completely disordered, but also have a TC that is also still similar. So then my question is that for your calcium doped, do you think if you have an ordering of the hole, do you think that that could actually have an influence on your result or not?
As my first thought is to reply yes, because I mean it will not only have so if you put some ordering on the holes, you will not only change the superconductivity but also the crystal structure underneath. Yeah, that's my answer.
Okay, yeah, I would say that you will create some type of periodicity within the chains, and that could influence some properties. But there for the neutron side, I don't know if there was a lot of study done on different. I'm sure it has been done, and I'm sorry if that I didn't look up earlier. It's just that I just came up with that question right now when I looked at the graph. How that will have how that does affect actually the result there. Another question I have about this topological superconductor candidates. It's very interesting, and I mean, I think everybody's chasing that because we want to have, let's say, super quantum computer and finding Majorana fermions, and this is really a hot topic. I was really, let's say, you did a lot of attempts to measure different ones, and I think that was nice that you put that in your thesis. That yeah, we tried, we didn't manage, but we got some. This is the I liked it. Usually thesis only shows only good result and denying the result that didn't work. And I think that was nice that you were honest there and put that. And I was wondering what, except sample size and having bigger crystal and better quality of crystal, what could be the other thing to improve to get significant result on these systems?
Okay, so thank you for remarking this, because the intention of including let's say non-successful experiments is because it's not straightforward the process to find a vortex lattice in a superconductor. So you will end up with a lot of unsuccessful experiments until you end up with a good sample and the good resolution of a certain instrument. So for the case of the lead, tantalum, and selenium-2, I think we were limited by the temperature limitations of the instrument. So we couldn't use, so we were using helium gas instead. So it only can achieve up to if I remember correctly, 1.8 Kelvin. And we were, I mean, the vortex lattice is much more easier to find it out if we reach millikelvin regime. Then also it's regarding to the sample, and it may be part of my fault. The samples were extremely thin, so they are really difficult to manipulate and really easy to destroy, either just by pinching them when putting on the aluminum plate that I show in figure 5.3. Then it's also how it's aligned, but we were quite confident with alignment of this kind of experiment, because we use another magnetic material to align the direction of the field, and then we put our sample. So that can be discarded. I mean, that can be discarded as a problem. And in the case, moving on to the case of gold to lead, this was just something that I had in mind many years since I was an undergraduate, and I really wanted to study this material. But the problem is that it has several structural changes when going down in field, in temperature, I'm sorry. And the thing is, like, before starting any kind of experiment, we have to align our samples with respect to the crystallographic axis. But if you have a structural change going down in temperature, you don't know what is going to be the alignment at the temperature that you are doing your experiment. So, also, if we take into account the quality of the sample and the regime that we're studying, etc., then it's quite difficult to see the vortex in those specific two cases.
I mean, regarding the alignment of the sample, I mean, I understand you have structural transition, but you should have somehow an axis, like maybe the c-axis that stays, remain the same. So in that case, I suppose that you orient at 300 Kelvin, and then you assume that your c-axis is always the same. And yeah, okay, there. This is how we. Okay, I see. I have a final question that relates a bit to one of the questions Sebastian asked you. So. So SANS is actually a transmission technique. And what you see is that you see an average of the vortex lattices, if I'm not making any mistakes there. And I was wondering, how do you think these vortex lattices evaluate as a function of depth? So meaning, how would that be that if you look at more on the surface or in the middle of the sample or more in the bulk of the sample, how and what do you think over technique can look? I mean, I think for the surface, Sebastian mentioned distance for the neutron side. I think in his talk, he's also mentioned over techniques to look at such vortices. So yeah, how do you think that can, influence in that sense?
According to depth, or according to the depth of the sample, it's quite, I would say it's quite challenging because you depend on the transmission of the sample. So if you have a material where your transmission is quite low and you decide to do, it's like you end up with not observing the signal at all if you have a really thick sample, for example. I guess it can be done because, as you said, like the superconducting properties can be changed dramatically if we just see into the surface or we see into the bulk of the sample.
All right, thank you very much, Emma, for answering my questions and clarifying points. Thanks.
Thank you.
Thank you very much, Jasmine, for your questions. And now we can continue here in the room. That also makes it a bit easier. But still, let me try to so also the so that one of my guests can see who is asking. So I would suggest that Pedro, that you continue first with your questions. Thank you. Yes, please.
Yeah, hi, Emma, thank you very much for the talk. It was very, very interesting and actually has solved many of the questions that I raised. Make my work easier. So, opposite to Jasmine, I don't know much about superconductors. I'm going to start with them. Something that has surprised me is something that in other magnets we regard as something quite small as the polyparamagnetism can have such a dramatic effect. So, do you think that there is any way of quantifying the effect of the polyparamagnetism in these materials and compare them with basically the coupling that the simulation gives? Basically, you can give a number for the polyparamagnetism in your systems and compare it with the simulations that you have used for doing the model.
I mean, that's actually the aim of our model, like quantifying somehow how the polymagnetic effects can be quantified in some sense. So just sticking to our model, we try to quantify or make a comparison between cerium copper silicon 2 and cerium cobalt indium 5, but we are still limited and under development because some of the fitting parameters that are meant to quantize or tell us about how this polyparamagnetic effect is parameterized. We have, for example, in the cerium cobalt indium 5, some temperature dependence that we were not expecting. So that maybe tell us that our model still is aiming an extra term to make everything temperature and somehow field independent and tell us information about it. So another thing, it would be nice to compare it with the theoretical values that I've shown previously and on figure. So for example, figure 3.9, because they actually use mu as a way to parameterize this strength of the polyparamagnetic effect. So it's the short answer is under development, and yes, it would be nice to parameterize and compare it with theoretical values as well.
Thank you very much. So you have said as well that the cerium cobalt indium is not at the end also the critical field, the second critical field is not limited by the polyparamagnetism. something else if I have understood correctly.
Could you please rephrase the question?
So if I understood correctly in your talk, you have said that the polyparamagnetism was not the ultimate limiting factor for the critical field on cerium cobalt. Maybe I've misunderstood you.
Well, I mean, both in cerium copper silicon 2 and cerium cobalt 5, we have these polyparamagnetic effects, which makes the magnetization and actually form factor to increase dramatically. And as I debated with Jasmine, basically they are, because of, we see this drop, but also for the cerium copper 2, they are candidates to show this FFLO unhomogeneous superconductivity on that area specifically. But yeah.
So regarding to the, especially to the dope INCO, so the 50% basically you don't see any distortion on the lattice. So it's a possible explanation that basically you are killing the D wave superconductivity and you just end up with S wave superconductivity.
That's actually a very good point, because we actually has been discussing, I've been discussing this with my supervisors, because the first thought when you see absolutely no change about a spinning effects happening on the sample, but it may be that by this whole doping, we are actually removing all the S wave contribution and ending up with the pure D wave contribution. It's another possibility.
So now I'm going to move quickly into some questions. So apparently I'm the bad guy here because I like time of flight. So let's go into
that's how we met, right?
Yeah. So this is a little bit linked with Sebastian's question about what fields would you like to go up and so on. So do you reckon that even if we have like this mass detector just for covering the angle that we need, and we will be able to measure the flux lattice lines? Maybe there is something else that you have to take into account.
Well, the pixel spacing also affects.
Just mind that you have the perfect detector.
Okay. You also need like you are also limited by the length on the instrument on the sensor.
As long as you want.
Okay. Instruments surrounding the actual instrument that may affect, like spin echo measurements.
Basically, my question is about the magnetic form factor. And the magnetic form factor decays quite rapidly with. So this means that even if you have this perfect instrument, you probably will not be able to see it. So what you will need in addition to that is a much longer wavelength. So still the angle is small.
Fair enough. Yes, absolutely.
And that actually links a little bit probably my last question, which is about your experiment on gold to lead. And I have noticed that you have measured at quite a high angles for what usually is measured in sun. So what was the reason for that?
So you mean with the rocking?
Yeah.
When
So you go basically from 1.5 to 3.
yeah, quite wide. Yeah. Starting the story, it's like we only had 2 days given for this kind of experiment. So when we first look at, we properly went down in temperature and the sample is already shaking and we are at the right field, we have to search the first rocking curve. So we usually start at wide angles, just in case the sample is not perfect, and because it can happen that the rocking curve can be quite wide. Still valid, but quite wide. So that was our. So indeed, the first rocking curve that we did, it was from -4 to 4 degrees, which is actually huge. But since we couldn't see any developing signal going up from the background, and then we became a little bit desperate. So we were just trying and trying.
Thank you very much.
Thank you. And these are actually questions from Dr. Diego Aldamineo. Sorry that I got your name wrong before. Martin, could you continue?
Thank you very much. So I'm not really a neutron guy. I'm very happy that I'm last, so that I can blame. I had a lot of really smart questions, but already by others. I also enjoyed reading your thesis very much. It's very nice. Well, Sebastian already talked a little bit, but maybe I want to dwell on it a little bit more. Of these topological superconductors and what you can actually see on them. I mean, do you think that you can see anything topological or not?
At the moment, not directly. So in the ideal way, in case we want to observe this P-wave superconductivity arising, but it's really sensitive to any kind of disorder. So at the moment, it's almost quite difficult to observe this P-wave. So what we do indirectly is so we mentioned that by conjunction with all the materials, we end up with a superconductivity, and for doing that, we need to be S-wave. So that's actually what we address here by using the beta Bismuth to palladium. It's like it actually follows S-wave S-wave behavior, and the vortex lattice is actually hexagonal, and we can address different superconducting parameters to characterize these kind of materials. So that's at the moment what we can do, just to go a step forward to see if it's actual and natural topological superconductor.
But did you say that the P wave is so fragile? Does that mean that we can stop hoping for topological superconductors?
No, no, but I mean,
is it a material restriction that you cannot see it, or is it the neutron restriction that you cannot observe?
As far as I read, it's kind of both, I think. And then also, again, depends on if you are relying on a layer on a boat, but from my perspective, I wouldn't say that we shouldn't lose any hope, because at the end, we need several techniques just to completely characterize a sample. So only one technique, like neutron scattering, is not going to be, it's not going to give the complete description of this kind of material. So it's just opening a window for the rest, I would say.
But if you had a perfect neutron source and a perfect sample, I'm a theorist, so
fair enough.
What would you look for them to tell if it's a topological superconductor?
The first thing I would look to it is how the vortex lattice should look like on that case, which I do not particularly know for a P-wave superconductor. And the second thing would be what I've been doing is like how the form factor evolves, so we can see if it actually. To be fair, I don't know how can be directly addressed with superconductor with one unit technique, apart from characterizing the vortex lattice and the form factor.
I understood this correctly. The sort of if these materials that you looked at, do you expect them to be P-wave throughout? P-wave something that dominates close to the surface, and then you have.
We were hoping to be S-wave, because in conjunction, it's when they end up with P-wave superconductivity. So to know that, it's like we want to know what are the values of the S-wave gap, how the form factor is behaving, or how the vortex lattice actually looks like. So we strictly wanted just to observe the vortex lattices for these materials, and if they follow the S-wave trend.
Yeah, so you're right that this bismuth palladium might be a topological superconductor. Why do you know why people have that suspicion? I mean, where does that come from?
So from the lead tantalum selenium 2 and the gold lead, they observe these Dirac points that are characteristic from these kind of materials. But in principle, for the case of the this beta bismuth to palladium, it's you have two different gaps arising under certain conditions, which is one related to the surface of the superconductor and the other one is related to the bulk. And that may be related to topological characteristics of the superconductor. And that's why it is aimed to be a good candidate.
Yeah, then you write, I think on page 71, you talk a little bit about these Majoranas that would then appear in multiple superconductors. You write that you would need to break spin degeneracy to get these Majoranas.
Mm-hmm.
Do you know why is that needed?
So basically as far as understood from the theory, is to observe these Majorana fermions individually. So we need this split, otherwise we see them in conjunction and we only see a Dirac particle.
Mm. Yeah, that's absolutely right. Maybe I can ask one last very naive questions. I know not so much about superconductors beyond, S-wave type stuff. So when you talked about the IPCO, you said that you had combined sort of D-wave pairing from these copper planes, and then there were some chains that you think gave you S-wave. I have a bit of a problem how to visualize this, because I would just see a big condensate of Cooper pairs, and all these length scales between some chain and some plane are much smaller than the superconducting coherence length. So can you even think about one pairing coming from one place and another pairing coming from another place?
It's not so strict. So there's some hybridization between the two. It's nothing so sharp in like this Cooper pair gives S wave and this Cooper pair gives D wave. So our guidance is how this superconducting gap looks like. So that's basically one.
Do you see this? Do you see it as a combination, just an S wave plus a D wave, or is it, as you say, to what degree is it some sort of hybrid? I guess you cannot isolate one and just look at,
What I don't. So could you please rephrase your question?
Recording in progress.
It's probably a little bit of a fussy question because it's all a bit fussy in my head. So I think I'm confused about how to think about this, how to think about something that has a combination of different pairings, where you say that one pairing comes from one place and another pairing comes from another place, and the sort of the extent of the Cooper pairs that is basically the coherence length is larger than any interatomic distance. Does it even make sense to say that one pairing comes from one place and another pairing comes from another place?
Well, we are certain sure that we are controlling the whole the change, and if we see this, so we are certain sure of some characteristics that are characteristics from the D wave and some other from the S wave, such as, for example, the hexagonal arrangement for the S wave or the square arrangement for the D wave. And if when controlling, for example, this whole concentration on the chains, and you see that it's a shifting to a square lattice, which is characteristic of D wave, that's what we are confident to say that, okay, this is something that there's an admixture of both pairings, that I cannot be on one.
Okay, then I think I understand at least where your statement comes from. I think I can be.
Okay, thank you very much. Now it's possibility to everyone in the audience to ask questions. Also, if you are joining via Zoom, please use the Q&A function if you want to add any question. Here, if I can. Until now, I don't see any questions in Zoom. Wait a bit more. Just need time to write. Otherwise, other questions here on site? Yes, please.
So thank you, Emma, for a very nice presentation. Just to answer Sebastian's question about the Bayesian analysis, yes, you could take the Bravais lattice into account, and it would be a very good thing to do because you'd be adding more information, and you're saying you've got information in one part of reciprocal space that's useful in other places, and you're reducing your parameter space, so you're concentrating more data into a smaller parameter space. So my question for you, Emma, is I see you did a lot of work on working with time of flight data. If you wanted to extend this analysis to time of flight, how would you start? Okay, maybe that's too difficult, but have you got any thoughts about that?
You'd have to take a few days off, so we can discuss this in. Like the main problem is, I mean, there's still something, but we need some grasp software developed for the TOF instrument first. But in principle, we translate our SANS analysis to grasp. And then for the Bayesian, the main problem I see is how do we balance, or how do we put certain weights for certain wavelengths? So here we put certain weights depending on the area of the Q space we are. But here, apart from that, we have to take into account. Maybe we can do that the same. Okay, so maybe instead, as a prior, we need to say what we expect the rocking curve is going to be. So in this case, we should need to give some prior on the wavelengths that we expect this vortex lattice to show up. That's my first guess. We can discuss later.
Yeah.
Yes.
First of all, Emma, thanks very much for your talk. And also, I'd like to say how much I have appreciated your enthusiasm and commitment to your research. That has been absolutely exemplary. And your rate of work preparing for this thesis has also been quite incredible. You have done a huge amount. Now, all of this is, shall we say, pure science. At the moment, you hold out the possibility, quantum computers and so on, but we're a long way away from that, probably with topological superconductors. What do you think is the usefulness of pure science?
I like that question. So I'm going to refer an example that some professor told me once. It's like if no one's never put a wheel on the floor and started rotating it, maybe the people surrounding that person would say, "Oh, that's stupid. Why you are rotating this wheel against the floor?" But then we end up with cars, with a lot of technologies that are based on the structure and the thing of the field. So basically, science is what opened us to, pure science is what opened us to several applications and enrich us, not only knowledge, but it can also enrich us in several applications in the future.
And it's fun.
Any more questions? have any questions on Zoom? All right, there is a last minute question here.
Thank you very much for the presentation and it was great. So we are confident that your thesis committee has tested your knowledge to the limit of physics. What I wanted to ask you is some knowledge to the limit of this world, if not the universe. And I know that I have promised that I would not ask any question today, so I would pass this opportunity to Annika. So what you will have is 5 very basic questions, and these 5 basic questions are relevant to an extremely challenging puzzle that you need to solve today. So let's welcome Annika.
Please tell me there is not the charge of the other plan.
As the beginning of this puzzle, I give you a teaser.
Okay.
And the first question that I have is that you can already guess what this shall be in the end. And after every question, you will get more hints to be able to answer this question.
Okay.
Okay, the first is this one.
Can I unwrap it or like?
Yes, please.
It smells like chocolate.
Oh yeah, that's already correct. That's one correct answer.
Okay.
And you can specify that more, I hope, later. Okay, that's already a good start, I would say. So now our more serious questions. Okay, Emma.
Yeah.
You know I like you, so if you cannot answer, you will still get more chocolate.
That depends on the question. Yeah, right.
So when was the shutdown of the HZB Newton reactor?
Unfortunately, it was in December 2019.
That's correct. Perfect. Get the next part, after which you can think about what this will be in the end.
I have a
And you
guess.
can assemble it.
Okay.
Yeah, please. After every piece you can guess. If you can guess already the whole part, then you can skip the question. If not, you have to answer every question.
Okay, we have to hear your questions.
I mean, you can guess now, and then I will ask the next question.
Okay, fair enough.
So it will be, it's a part of a puzzle. And in the end, it will be one whole structure. So you can guess what it could be.
Fair enough.
Of course, it's chocolate, but it's something.
Okay.
Okay, then I ask the next question. What is this? Ailuropoda melanoleuca. What is that? It's Latin, by the way.
Can I switch back to Sebastian's question, please?
Sorry, no.
Please repeat.
Ailuropoda melanoleuca. And yes, I tried that.
Can you read it?
I can write it maybe. Yeah, there's a reason why I didn't write the text for your cut.
I am definitely not going to pass this thesis.
You'll be so surprised when you discover.
But then you're lucky, you have the chance to pass the answer for this question to the end of the puzzle,
Okay.
because it will be related.
Okay, but can I know the meaning of that or not?
Yeah, then you have to guess again after the end of the puzzle, because then you will know what it means.
Okay.
So this is the next part. part, if you feel able to guess.
I may know what it is.
Oh, okay.
Okay, but I will, okay.
You can start guessing, I think.
That's the Greek name for panda there.
Nearly. Very near. It's Latin. It's correct. Perfect. Then I have one more question to you to get the next piece. How do you translate your name to English?
Emma.
So,
Oh, my surname.
Yeah.
Tesla.
Yeah.
Or small field.
This is the next piece. I hope you will be able to assemble it in the end.
Okay. I have much more parts than I was expecting.
After this, I have one last question. Okay, the last question is maybe the most difficult and you need to guess, I think. Yes. What is the maximum field value that the 17 Tesla magnet has ever reached?
I would say 17 because then it will quenched. So,
and no, it's not 17.
I would say 16.5.
Different direction.
16.8.
In a different direction.
16.3.
It's higher than 17.
It's higher than 17.
And I asked experts for this. Maybe he can comment on it.
Alex, you
Yeah, 17.7 by accident.
And did it quench?
It did quench, yes.
It's not
And we were
valid.
told never to do it again.
So now you will get the final last piece and you can assemble it.
Okay.
And yes, you already know the answer to this question. Oh, I don't want this way.
Help. Oh my God. Wow.
You know what?
By the way, fully eatable.
That's the problem. I don't want to eat it. Only lighters.
This day is very important, so I try to keep it.
I apologize because the audience may be quite hungry. But
This is the good thing. I have several pieces of all the small parts. And you can eat one version and keep one.
We see its face.
That's good. I have several pieces. Yeah, but I can help you to stick it later.
Okay.
Don't worry.
I didn't know that pandas have.
Okay, these are some leftover pieces from the eyes. Because it was just the teaser.
Thank you.
Welcome, but because you're lucky today, from all the small pieces you get several parts. So you you can feel free which to eat and which to keep. And because we know that you like more darker chocolate or milk chocolate than white chocolate, the white is painted.
Oh, thank you very much.
I think you have passed also our questions, so.
After this most difficult part, I close the defense here at this point. Thank you very much. Thank you very much to everyone who was involved and to everyone joining here. I now would like to ask the committee members and also the opponent and the supervisors to gather in the separate room, H42 here. Also, we need to have use the link from Zoom provided. The audience, everyone is invited to join Emma afterwards to the lunchroom of our division in the top floor of the K building. Thank you.